Okay, so today we're going to talk about the last chapter of this book, which is the partial differential equations. Partial differential equations is different from what we learned in chapter 4 and chapter 10, chapter 9, and where we have handled the so-called ordinary differential equations, or ODE. And here, chapter 10, we discuss the PDE. The difference between ODE and PDE is very simple. In ODE, we always have only one variable. One variable means that, you can call it whatever you want. It could be YT, could be YX, or as we learned in chapter 9, when we deal with high order differential equations or general first order equation arrays, it always looks like something y1t to ynt. So here, whatever it is, x, t, or t here, there's only one variable. However, so in the case of PDE, we need to deal with functions that depends on more than one variable. Again, the name of the variables doesn't matter, and I can call one is called x, which is space, the other is called time, or I can have multiple spatial variables. As far as we know, so far we only know one time variable, or maybe we're dealing with a steady state, so there's no time variable. It can also be that this u is not a scalar, but a vector, so that it contains more than one component. So all of these are examples for the PDEs. So because of the dependence on more than one variables, we cannot just take derivatives, say ddt anymore. We need to be specific about with which variable we're taking the derivative. This is called the partial derivative. For example, without loss of generality, we're going to just consider this case, one-dimensional space, one-dimensional space and one-dimensional time, partial u, partial t. This one, it is really, we take a limit, let's say u x, only along the time direction. We move by a tiny bit, delta t, minus uxt, and compute this ratio with respect to delta t. And I let delta t go to 0, and I defined the partial derivative with respect to t. In particular, here x stays put. Similarly, I can consider partial x, partial u, partial x. The definition is exactly the same, but now the infinitesimal change is moved along the x direction, and the t variable stays put. I divide by delta x. Any question? So just like the ODE, we can take partial derivatives of a higher order, xt, and this one is, the definition is you take a partial derivative over another partial derivative. So by definition, this is limit delta x go to 0. This is partial u, partial x, x plus delta xt, very much analogous to this thing, and minus partial u partial x xt delta x, so on and so forth. So you can define higher order derivatives in this way. So now we have assumed we always deal with functions that are sufficiently smooth. If it's not smooth, we're going to study that later. Then all the derivatives with respect to t and x have been defined. Then we just put all these derivatives together, we get an equation, and subject to proper conditions, not only the initial condition, but also later we're going to learn called the boundary condition. There are many ways to put these derivatives together, and given the time, which is about a week, it would be pretty crazy for us to go through more than one of those. So we're going to be loud and clear that we focus on one PDE. This is the only type of PDE we're going to care about in this class. For the heat equation. In the book, there are also wave equations and Laplace equations. Because of the time, we won't talk about them. So the heat equation, we start from 1D. This is physics. This is called the Fourier's law. I won't derive it here because it will be tangential to our interest of this class. And in the book, there's a short derivation how this law comes from. We're going to directly write it down and just think that this is just a way for us to put two derivatives together. In particular, on the left-hand side, it is the first order derivative with respect to t. On the right-hand side, it is a constant called beta times the second order derivative with respect to x. Here, beta is called the diffusion coefficient, and it is always a positive number. Later, we're going to see that the fact that beta is bigger than 0 is very, very important. So what's the physical meaning of it? It describes the following process. Let's say that we have a rod, one-dimensional rod of length L, so that I can parameterize each point on the rod by a number x between 0 and L. And now I look at any point here, which is x. I have a function uxt describing the temperature. The temperature of this rod at this point. So let's say that this rod is made of iron, and you can imagine that if I just have something, I just heat it up exactly here, then so this part is going to become hot, but later the heat is going to dissipate towards the boundary as well. So the heat equation exactly describes such a process. So for simplicity, I mean, this one is a non-equilibrium process, so they have an external source. Let's forget about this thing. We just say that somehow you have heated this rod up so that there is an initial temperature distribution called the ux0, because at time t equal to 0, indeed, each point on this rod has a certain temperature. And what we're interested in is that at time t, what will be the temperature of this rod? If I just talk about the setup of the problem like this, it doesn't make sense. Why? Because I didn't talk about what happens to the boundary. Which is, in this case, x equals to 0 and the x equals to L. Why does the boundary matter? Think about it physically. I mean, I can, for example, I just have put 2 ice cubes here so that it absorbs enormous amount of heat away from the 2 endpoints. Or I actually put I heat this thing up constantly around the boundary, and the effect of the 2 things will be absolutely different. So the boundary is for PDE is always very important. And in this case, for simplicity, we set the boundary to be U0T equals to ULT equal to 0. So you can think like I put 2 freezers the boundary so that any positive temperature is going to be sucked away from the boundary. But it's not like sucking away the energy at infinite speed. It will be governed by the law of the physics. So, and when I take U to be 0, that is particularly convenient because the equation becomes homogeneous. So indeed, if I remember that what's a homogeneous equation, we always discard the initial data. And so we look at T equals to beta, this thing, U0T for all T equal to ULT equal to 0. Assume that UXT is a solution. And the hallmark of a homogeneous equation is that if UXT is a solution, then any constant C times UXT is also a solution. This can be easily verified. On the left and right hand side, I multiply by C. So indeed, CU satisfies the heat equation. And now for the boundary data, I multiply by C times 0 is 0, and indeed, it satisfies the solution. It will be different though, if let's say I put a freezer 0 on the left-hand side, a furnace let's say ULT is always kept to be 100, then such kind of scaling invariance property wouldn't hold, and that corresponds to an inhomogeneous equation. Now, starting from chapter 1, I mean, from the very beginning of this semester, we have gone through this iteration, this mechanism for a couple of times now. Whenever we see that there is a homogeneous part and there's an inhomogeneous part, we always first study the homogeneous part. We study really the process to death. We figure out all the possible linearly independent solutions. And there will be some unknown coefficients, presumably to be determined by the initial data or some other things. And later, when we look at the inhomogeneous equation, we're just going to find some particular solution and then to add the corresponding homogeneous contribution. Does it make any sense? Okay, so now from now on, we're going to focus first on this homogeneous setup. This particular way, this is not the only way, by the way, to set up the homogeneous equation. By setting the function value to be 0, which means that the temperature of those 2 points are kept fixed. That must be 0, regardless of what's going on. For the rest of the rest part of the rod, the 2 ends, the temperature are set to be 0. And this is called the Dirichlet boundary condition. So I can have other types of other homogeneous equation or boundary way of setting up the boundary. The equation is exactly the same thing, but I can say partial u partial x 0t equals to partial u partial x lt equals to 0. So what does that mean? So this one, partial u partial x, is like, what's that? So it's like here it is the temperature to 0. Here it is the temperature at delta x. The difference of the temperature divided by x, partial u partial x 0t, means the heat flux, because, or the temperature difference. So so if there is a heat flux, then if it is non-zero, then heat can flow from one place to the other. But if I set it to be 0, it means that there's a no heat flux. So unlike I'm setting a freezer there, saying that the temperature must be 0, I don't specify u. I don't know at this point what is the value of a u 0t. But what I'm saying is the heat cannot escape from the end of the rod, nor will any additional heat be injected to the end of the rod here. So this one means that the physical meaning is that the rod is insulated from the environment. Because on both ends, it cannot go away or new heat can come in. And mathematically, this kind of data saying, boundary data saying the derivative vanishes on the boundary is called the Neumann boundary condition. And this von Neumann is not the von Neumann that many of you know, who invented computers and other things, but different Neumann, earlier than von Neumann. So, so the treatment of the Neumann boundary condition is going to be very similar to the treatment of the Dirichlet boundary condition. So the Dirichlet boundary condition would be a particular focus. So let's pause for a second and review what we have said. We started from something that is rather general. I say we started from PDE and say there are many ways to put the derivatives together. And then I said, we're only going to focus on one way of putting the derivatives together. This name is called the heat equation. It looks like this. And then we temporarily forget about the initial data and only focus on the boundary. We realize that just due to physics, there are many ways to set up this problem by setting up different boundary conditions. I give you two examples. One is to set the temperature to be fixed at the boundary. This is called the Dirichlet boundary condition. And the other is to say the flux is known, but I don't know precisely the value of the temperature. This is called the Neumann boundary condition. Now we're going to focus on a very, very specific thing, which is heat equation, homogeneous boundary condition, and in particular, Dirichlet boundary condition. Okay, my claim is if you understand this thing, which is the most important thing in this chapter, then the rest of the examples will be much, much easier to understand. Any question? Okay, so let's now solve this problem. So let's now solve this partial u partial t u 0t equals to u lt equal to 0. So I would like to, before we actually solve that, I would like to again connect it back to linear algebra. So as I said at the beginning, when we talk about the ODEs, I mean, this class is really, you put the two books together, and in principle, I mean, it could be related, it could not be related, depends on where you study this. Because we're in Math 54, we're studying this class called linear algebra and differential equations. So I feel kind of obliged to fabricate some reasons to convince that they are indeed connected. So let me show you how they are connected. The fabrication is very similar to the argument I made for the ODE, which is we look at a vector space, which is an infinite dimensional thing, and this vector space is V. Let's say I just consider this Fx, forget about T for the moment, where this F is infinitely differentiable. Let's call it smooth. And a smooth function plus a smooth function is still a smooth function, together with a boundary data. Okay, so I consider this is a vector space. So addition of the two, if it vanishes on the boundary, the linear accommodation still vanishes on the boundary. And now I would like to consider an operator. I call it A. This is operator, or you can call it T. So this A, so this, let me call it A. So A is operator from V to V. What it does is, let me call it T to be consistent with what I had before. And this one is Tfx, is the second order derivative. So this one you definitely have seen. The only difference is that now instead of call it f double prime, I call it d squared dx squared. I can also call it partial derivative if I want, but here I only have one variable. Now, what I'm going to do is something that is maybe slightly a little bit difficult to understand, which is we think, okay, this uxt, I fix this t for a fixed t, and then this guy is x, and I would like to tabulate all the possible x. You say, well, this is not possible because there are infinite number and actually uncountable number of x, but I'm going to explain later why this makes sense. But for fixed t, this indeed can be thought as a function of x, as a single variable function of x. Then this thing for fixed t, and it belongs to V. Why it belongs to V? I said it's smooth enough, let's assume that, and it satisfies the boundary. Is that going to be okay? Okay. The next what I'm going to do is to say what do I mean by tabulating it? Tabulating means the following thing. So I have a 0 to L, and now instead of think this is a function on infinite number of points, I discretize. I only look at these points. Let's say I only look at u xi t, where xi is, let's say, I minus 1. There are n of the n points. So let's say n minus 1 times L, okay? Where I runs from 1 to n. So immediately I have x1 is 0 and xn is L. So I have n points here, uniformly discretizing the space. Now you can think that if I have a smooth function here, then as this n goes to infinity, then at some point it will be so difficult for me to figure out the difference between this continuous function and the u evaluated on this point, because it's a smooth and the difference between these two is very, very minimal. So then I can think that there's a vector u. So this u consists of u x1 t da, 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 u xn t. So the solution of the PDE would be very, very similar to the solution that I obtained by looking at this vector, which is of length n for each t. Does it make any sense? I want to say that this has nothing to do with how you solve the problem. I just want to give you a linear algebra perspective to connect the PDE part in a as close as possible way to the ODE and to the linear algebra we had before. So this one now, I've converted this thing that depends on two variables by discretizing the space, but without discretizing the time. And I converted this to a single variable, a vector that depends on a single variable t. And now I look at the look at the heat equation, because this one only, you see, this partial square, this double derivative with respect to x, it only acts along the x direction, right? So just as we had before, you have collapsed this infinite dimensional thing to a finite dimensional space. Therefore, this T will have a corresponding matrix representation, so that the heat equation is similar to something like this. ddt ut equals to a ut, where this a is the finite dimensional representation of the beta t operator, which only applies to x. Any question?
Why does A apply to t but not to x like before?
No, A actually, this is a matrix vector multiplication. So by doing a matrix vector multiplication, A times U here, you see this T is fixed. So it exactly means that it only applies to X. Right? So we have, this is a matrix A, applies to U x1t, da 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 U xnt. Let's look at the first row. The first row is exactly summation j a1 j u x j t. You see, it is really an operator acting on the x dimension. The t is fixed. Did that answer your question?
Yes, thank you.
Any other question? Okay, so what is this? This is really what we just learned in chapter 9. So in particular, if A is diagonalizable, if A is diagonalizable, and with a lambda, with an eigenvector, let's say, called a lambda and corresponding vector called V, then immediately we have u t equal to exponential lambda t vt is a solution. And sorry, so I should say that, this. If A has eigenvector equals lambda b, then ut equals to exponential lambda t vt is a solution. If A is diagonalizable, then we can find u1t equals to t v1t unt equals to exponential lambda nt vnt, and this will be a fundamental solution set. So that you give me any initial condition, I have a fundamental solution set. I just do a linear combination and solve it. Sounds a little bit abstract, but what we're going to introduce next, called the method of a separation of variables, is exactly this. Without going through the justification above. But the justification above is just to tell you that looking from this perspective of a method of a separation of variables, the PDE problem looks exactly like an ODE problem. Let me explain why. So this discretization is just to convince you that there's some connection with a finite dimensional ODE, because otherwise I could throw an infinite number of vectors to you. That's pretty tough. But now we directly, so the method of the separation of variables, the starting point is this. We start from this eigenvalue problem. Why? Because once we solve the eigenvalue problem, and find the eigenvectors, we immediately find that there is a solution to the heat equation. Then once we have this so-called educated guess, we may just plug in the equation, plug the solution into the equation and verify that it is correct. So how do I do that? What I want is this t, which is without a discretization. Now I call it I don't call it v. Let me call it this capital XX, which is a function equal to lambda capital X, subject to the boundary condition, because capital X needs to belong to the space V, means that the boundary condition needs to be satisfied. Remember that this T acting on that is nothing but X double prime X. So,
Professor, what is the capped X?
It's just a function. It's an eigenfunction. So it plays the role of the Vx before. But since I don't have this vector, I just call it a function, capital XX.
Okay.
Yeah. So like the justification above shows that shows why I want to care about such an eigenvalue problem. Now I solve this eigenvalue problem, but this is an infinite dimensional operator. So it's I need some other way other than linear algebra to solve this. So this is an infinite dimensional eigenvalue problem. Okay.
Okay.
So this infinite dimensional eigenvalue problem sounds extremely scary, but not really, because what I'm doing here is minus lambda XX. Lambda is unknown. That is a little bit scary. And it's not initial data. It's boundary data. It's a little bit different. But other than that, this is a one-dimensional ODE. One-dimensional second-order This is just a second order ODE. So, so we know how to solve this. So there's the so-called auxiliary equation, and tells me that R1 is lambda, R2 is minus square root of lambda. So it might be that they are they have repeated roots or lambda is negative. So naturally, we need to discuss 3 cases. Case 1 is lambda is bigger than 0. Then for any fixed lambda, I don't know the eigenvalue at this point. You might say, okay, this is the eigenvalue problem. Now I need to compute the determinant and the blah, blah, blah. But this is an infinite dimensional problem. So we cannot really use the method like determinant we had before. We need to use this new tool learned from chapter 4. So once lambda is bigger than 0, all the possible x would be C1 exponential x, C2 exponential minus lambda x. But this C1 and C2 should be constrained to satisfy the boundary data. So in order to have x0, this is C1 plus C2. So means C1 equals to minus C2. But also we have the boundary data XL, and this one is C1 exponential lambda L plus C2 exponential minus lambda L. They are both 0. And because this matrix 1, 1 exponential lambda L exponential minus lambda L, this is invertible. Compute as the determinant is not 0, unless L is 0, but then the rod has length 0. That's not interesting. So it's invertible. It means that the solution is trivial. So we're done. This is not possible. Everyone got the reason why it's not possible? Good. Second case, lambda is equal to 0. And in this case, we have repeated root. If it is a repeated root, then one solution should be just an exponential 0 times x, which is a constant. The other one is x times that, so it's a linear function. Again, check the boundary. This one tells me C1 should be 0. This one tells me C2 should be 0. So again, C1, C2 equals to 0, 0. And the eigenvector cannot be a 0 vector, so not possible. If it turns out that we have ruled out the case lambda is smaller than 0 and still 0, 0, then we just declared that this problem is not solvable. But let's try. If lambda is smaller than 0, we have a pair of complex roots that are conjugated to each other. Because we look for real solutions, we now should be pretty familiar, and we can consider the cosine and sine representation. X. So has a minus here, so that this is a positive thing, and so that this cosine sine takes care of the I according to the Euler formula. Then 0 equals to x0 equals to C1. Okay, seems to be bad news. So 0 equals to XL equals to C1 is already equals 0. Forget about that. So this is C2 times sine minus lambda times L. You might say, yeah, sine square root of lambda minus lambda L is is not 0, so C2 is 0, so that. Not really. It seems like in this very last term, we found our hope. Because if this guy is pi times an integer, n plus means 1, 2, 3, 4, not 0, because then you're going to have 0. Then this is 0 equals 0. So then C1 is 0, but C2 can be anything. If C2 can be anything, in particular, we can take C2 to be 1, then this sine function indeed satisfies the solution. And you see, this eigenvalues, it's not like you give me any lambda, there's going to be a solution, but for some particular negative lambda, indeed, there could be a solution. So labeled by this n, we find that minus lambda n equal to pi n. So this trick is indeed new, although the general framework, as I said, is very, very similar to chapter 5 when we diagonalized and chapter 9 when we saw ODE's first order equation arrays. But this trick is new, and this lambda n is therefore minus sign is extremely important, and this is a pi n divided by L squared. Correspondingly, the solution is sine minus that square root, so pi n divided by L x. The constant doesn't matter. Any question? So now let's say that if you're suspicious, let's check. So first of all, we check that this is indeed an eigenfunction. All you need to do is to take second order derivative. So indeed, you take this, you have a sine, take a derivative becomes cosine, cosine derivative becomes minus sine. So this is a minus pi n divided by L squared times sine. So indeed, x and x, good. So satisfies the equation. And if you look at x and 0, this is naturally 0 because sine 0 is 0. If you look at x and L, this is sine pi n is 0, so this is good. Indeed, this x and x satisfies both the equation and the boundary. Now let me make an educated guess. Full solution of heat equation. Which means that following exactly the same principle, like a long time ago, following exactly the same principle here, I've already found an eigenvalue, which is labeled by n, eigenvector, I call it x and x, again labeled by n. The solution must be exponential of this eigenvalue times t, sorry, there's no t here, times this eigenvector. So there's no t here either, typo. So the solution, if I want to make a guess, I still need to verify it later. It should be exponential minus pi n divided by L squared times x n x. So let's check that. So check. Obviously satisfy the boundary data of the t. Obviously it satisfies the boundary data because only this part depends on x, and we have to verify. So all we need to is to check it satisfies the heat equation. On the left-hand side of the equation is derivative with respect to t. So this is minus pi n divided by L squared, and this is times x times uxt. And the right-hand side is double derivative with respect to the x. We have just done that here. This is indeed beta. This is indeed beta square xt. So we're done. Any question? So this one, let me call it UNT. It's a solution to the heat equation. By superposition principle, uxt equal to n from 1 to infinity, Cn un xt is also a solution where this is C1 to infinity. We have an infinite number of things needs to be determined. How do we determine that? We match the initial data, which means that you give me a u x0, this function is known. I want to match it with respect to un x0, but un x0 is nothing, this is 0 here, but xn, this is Cn. What's xn? Xn is pi n divided by Lx. So for this known function, ux0 is expanded using these sine functions, and this is the so-called Fourier analysis, or more specifically, the Fourier series. And we're going to talk about that. Next week. Any question?
A question about the